today I'm going to talk about some very recent work I did with Pingan Cheng from Aarhus and David Zheng from Illinois, which has just been accepted to SOTA. Okay, so the topic is Voronoi diagrams. So let me begin with what everyone here already knows, I'm sure. So the standard Voronoi diagram. So you're given endpoints in the plane, and we're looking at the planar subdivision where you put 2 points in the same region if they have the same nearest neighbor under the Euclidean metric. Okay, and the picture you see here was hand-drawn, and the caption was typewritten, and it was not done by me, but it's from the seminal classic paper by Ramos and Hui back in the 70s. So although the concept of Voronoi diagrams date back even further, Ramos and Hui's paper is famous because it was the first, I guess, to introduce or popularize the notion of Voronoi diagrams to the theoretical computer science community. And it also contains the first optimal analog n algorithm for constructing Voronoi diagrams in the plane by divide and conquer, as I'm sure many of you would remember. So the problem we're going to study here is actually a generalization of the problem, namely the order K Voronoi diagram. And it's defined in a similar way. So we're looking at a planar subdivision where you place 2 points in the same region if they have the same set of K nearest neighbors. So that means the first K nearest neighbors are the same, ignoring the order. Okay, so this picture shows an order 2 Voronoi diagram. So again, it's taken from that very same paper by Ramos and Hui. So I find it interesting that the original paper already described this generalization, and showing that this generalization is actually very natural and very basic. Here is a slightly clearer picture, which was taken a few years later from Ian Ramos' PhD thesis, which is commonly regarded as the first thesis introducing the area of computational geometry. So literally, the order K Voronoi diagram dates back to the beginning of computational geometry. And by the way, throughout the talk, I'm going to assume implicitly that K is at most n over 2, and that's because if K is bigger than n over 2, we can replace K with n minus K if we switch from nearest to farthest. And everything we're going to talk about, all the algorithms extends, even if we're talking about farthest neighbors rather than nearest neighbors. Okay, so let me briefly go over some well-known properties about the order K Voronoi diagram. Each Voronoi region, as you can see from the examples, is a convex polygon, where the edges are defined by bisectors of pairs of points. And the size, the combinatorial complexity of the diagram, namely the number of regions, edges, and vertices, is known to be theta of n times k. And that was first proved in the classic paper by D.T. Lee. And this is known to be tight, not just in the worst case, but also in the best case. So the question we're going to address is the algorithmic question. How fast can you construct the order K Voronoi diagram? And surprisingly, this has remained open till now, okay, despite the long history of the problem, as I've said. Okay, so for those who are familiar with the concept of K levels, let me mention that the order K Voronoi diagram is equivalent to the K level in an arrangement of n planes in 3D, where all the planes are tangent to a paraboloid. And this is because of a standard lifting transformation. So the K level is defined to be the subarrangement consisting of all points for which there are exactly K minus 1 objects below. the point. Okay, this is obviously a picture in 2D because I can't draw well in 3D, but you get the idea. And to see the connection, all you have to do is map each of the input points A, B to a 3D surface, Z given by essentially the Euclidean distance of x, y to A, B. And it's not easy to see that the order K-Voronoi diagram corresponds to the K level in an arrangement of these surfaces. But of course, these surfaces are not planes, but you can get rid of the square root and expand the expression, and notice that x squared plus y squared is a common term, so you can pull it out, and then you get a linear expression. And so indeed, it corresponds to K levels of n planes in 3D, where all of these planes are tangent to the paraboloid z equals minus x squared minus y squared. Okay, now the combinatorial complexity of the K level is notoriously hard, a difficult question in combinatorial geometry. It's equivalent to the K-set problem, as some of you know. But in our case, all the planes are tangent to the paraboloid, so they all bound their lower envelope. So in a sense, they are in convex position. And in the case of planes in convex position, indeed, the combinatorial complexity of the K level is much easier to bound, and it's precisely n times K. So all the algorithms we're going to describe actually will generalize to computing the K level of any set of n planes that are in convex position. Okay. All right, so this is a fundamental problem. So you expect lots of applications, and indeed there are. So I guess the first thing that comes to mind might be, from the definition, might be data structures for finding K nearest neighbor, for doing K nearest neighbor search. But actually for K nearest neighbor search, there are more space efficient data structures using a different concept known as shallow cuttings. But still, there are some genuine applications of the order K-Voronoi diagram, like finding a subset of K points with the smallest variance and so on. Okay. All right, so let me now do a quick survey of previous algorithms for the order K-Voronoi diagram. So Lee's original paper not only gives combinatorial bounds on the order K-Voronoi diagram, but gave the first algorithm running in nk squared log n time. Okay, and this was subsequently improved to n log n plus nk squared. And these algorithms actually compute not just the order K-Voronoi diagram, but all the diagrams from order 1 up to k. But if you just want the order K-Voronoi diagram, no one forces you to compute all the lower order diagrams. So there are faster algorithms. Okay, so for example, Giselle in 86 gave an algorithm with runtime nk times square root of n, roughly. And Giselle and Eels-Bruner in 85 gave an algorithm with runtime n squared plus nk log squared. Okay, and this is obtained using the following idea. So the 3D K-level problem can be reduced to n instances of the 2D K-level problem. And then the 2D problem is solved by using data structures for dynamic 2D convex hull. Okay, and at the time, the best data structure for dynamic convex hull has 2 log factors by Overmarsh and Van Leeuwen, but this was subsequently improved to 1 log. Okay. Ken Clarkson in 86 gave a different randomized algorithm with runtime that is close to n times k, but with an extra factor of n to epsilon. But the advantage is that there's no extra n squared overhead term. Okay, and this was done using random sampling-based divide and conquer. Then later, Agua and Matusha gave a deterministic algorithm with essentially the same runtime. And the idea this time is to directly use dynamic 3D comics hall data structures. And if you use the latest current best data structure for dynamic 3D comics hall by yours truly, then the anti-epsilon factor can be lowered to polylog. Okay. But even better algorithm was proposed by Agarwal, de Berg, Matushik, and Schwarzkopf. And there they suggested a randomized incremental approach, and they got n log qn plus nk log n. Okay, so the idea is to insert input points one at a time in a random order and maintain some superset or neighborhood that contains the k level. Okay, and then this was later improved in a paper of mine to n log n plus nk log k. Okay. And then finally, Ramos in '99 further improved this to n log n plus nk times 2 to the order log star. Okay, and this is very interesting. So log star is the iterated logarithm function. So it's the number of times you apply log to bring a number down to a constant. So it's extremely slow growing. So Ramos' algorithm is extremely close to being optimal. Okay, because nk is the output size. Okay, great, but a question still remains. Okay, so theoretically, can you completely get rid of all the extra factors? Okay, get rid of that log star to get truly optimal runtime. Okay, and more than 20 years later, we finally answered that question positively with a new randomized algorithm with runtime n log n plus nk. And that's the main result that I want to talk about today. Okay. All right, so if you're familiar with some of my previous work, then you might have seen that I have also shaved log star factors before for other problems like Cleese measure and for a half-graphs problem. So I don't want to be known as the guy that shaves off just log star factors, but the order K-Voronoi diagram problem is different, so it will use interesting new ideas, building on earlier work on half-graphs. Okay. All right, and I should warn you ahead of time that this is purely a theoretical result. Okay. So first of all, log star is for all practical purposes a constant. So and the new algorithm is going to be very difficult to implement for reasons that you will find out, and the hidden constants will be huge. Okay, but still, as I said, the problem is fundamental and dates back to the early days of computational geometry. So it's important from the theoretical perspective to really nail down what the true complexity of the problem. Okay, and if you want an analogy, for example, Chazel's famous linear time triangulation algorithm for simple polygons. That was a result about shaving out log star because at the time, the best previous algorithm for triangulation has runtime and log star n. Okay. All right, so any questions so far, by the way? Feel free to interrupt if there are questions. So I'm going to describe the new algorithm, but before I do so, I'll begin with some preliminary facts that we're going to use later on. Okay. So the first fact is that in n log n time, you can reduce the order K-Voronoi diagram problem to n over k instances of size order k. Okay, so and this was first shown in my paper from '98 using random sampling or shallow cuttings, and this was later de-randomized. Okay. The importance of this fact is that to solve the order K-Voronoi diagram, it suffices to concentrate on getting good runtime as a function of n alone. Because if you can get an algorithm with good runtime in terms of n, t of n, then you can just plug in t of k into this formula, and you automatically get good bounds as a function of both n and k. Right, so for example, if you look back at all the previous algorithms, you'll see that in terms of n alone, Chazelle and Adolf-Spooner's algorithm is actually not too bad because that's n squared log n, right, as a function of n. Similarly, Aarhus, Berg, Matuschik, and Schwarzkopf's algorithm has runtime n squared log n. So then if you apply my reduction with tk being k squared log k, put that into the formula, then automatically you get n log n plus nk log k, which was the result in my paper. Okay. And then subsequently, Edgar Ramos showed that in terms of n, he got an algorithm with runtime n squared times 2 to the log star. And then by applying my reduction, then that's the way he got the final bound of n log n plus nk times 2 to the log star. Okay, so all this means that if you want to get an optimal algorithm for order k Voronoi diagram, it suffices to get good algorithm as a function of n, namely an algorithm with runtime n squared. Okay, because if you can get n squared, then you can just plug in the formula and you get n log n plus n times k.
Okay. May I ask a question?
Yes, sure, please.
What do you mean by the one parameter? Do you mean that
in terms of
k is arbitrary?
Yeah, yeah. So for any k, so basically the worst case is 1k is theta of n. So for the so it suffices to concentrate on the case where k is theta of n, basically.
Thank you.
Okay. All right. So then that's what we'll aim for: getting a quadratic time algorithm, okay, and squared algorithm for the problem, and then the result will follow. Okay, so that's fact number one. Here's an even more important fact due to Ramos, and it's a self-reduction. So it says that in n squared time, you can reduce our problem, order k Voronoi diagram, to n squared over log squared instances of size log n. As a result, you get this recurrence. Okay, and the way Ramos achieved his result is actually by running the previous algorithm by Aarhus, Berg, Matuschik, and Schwarzkopf, the one based on randomized incremental construction. And except you run it only for up to n over log squared, n over log n steps. And because you stop early, then the runtime avoids the extra log factor. Okay. And what he observed is that at the end of the algorithm, when you stop early, what you end up with is actually a cutting where conflict list size is log n, and the cutting covers the k level, and hence you get this reduction. Okay, it's not important to know how the how this is proved, but this fact will be essential for us. We're going to use it multiple times. Okay, so in particular, Ramos then apply his recurrence for log star iterations to get input size all the way down to a constant, and hence he got n squared times 2 to the log star. Okay, but we want to avoid the log star factor, so we can't afford to use this recursion all the way down to constant input sizes. But still, his recursion will be very useful. In particular, there is a very strange consequence of Ramos's self-reduction, and it's the following. If you can find a good decision tree to solve the problem with n squared height, then automatically you can get an algorithm that runs in n squared time. Okay. So for those of you who don't know too well about decision trees, basically in the decision tree model, we're just looking at counting number of comparisons made by the algorithm. So comparisons means testing the signs of algebraic functions of constant degree. Okay, so we access the input elements only through such comparisons. Cost is the number of comparisons made. Everything else has zero cost. Okay, so in the decision tree model, if you can get a good result, then automatically we can turn that into an algorithm where the actual runtime is bounded by n squared. So that's a claim. Okay. So why is this true? Simple proof. You just apply Ramos's recursion, say 3 times. Okay. Then that will bring the input size down to triple log n. Okay. Then for input size that small, you can actually afford to build explicitly the whole decision tree. Okay. Now, normally the decision tree will have super exponential complexity, but for input size this small, something that's super exponential in triple log n is tolerable, right? And then once you have the decision tree, then all of the small size of problems can be solved optimally in log squared time. And so the total time will be log squared. And approved, okay? So then that means from now on, it suffices to concentrate on coming up with good decision tree to solve the problem. Okay. Is that clear? Any questions? Okay. All right, so then in the rest of the talk, I'm going to describe the new solution, and it will be in 2 parts. So in the first part, we're going to reduce the problem of constructing order K-Voronoi diagram to verifying order K-Voronoi diagrams. And this will be the crazy part because it's going to use decision tree techniques, and it's going to use some rather unusual ideas that to a theoretician you might find fascinating and cool, okay? But to a practitioner, you might cringe, okay? And then in the second part, we'll solve the verification problem itself, and this part will be more traditional, based on more normal ideas, more down to earth. Okay. So I'm going to start with the crazy part. Okay. All right. So what we're saying is that the problem of computing order K-Voronoi diagrams reduces to verifying. Okay. So claim is if there is a quadratic time algorithm to verify whether a given diagram is the correct order K-Voronoi diagram, then you can actually get an algorithm to quadratic time algorithm to compute the order K-Voronoi diagram. So you can solve the easier problem of verifying, you can actually compute the order K-Voronoi diagram in the same time and square. So that's the claim, okay? So let's take a moment to see how really shocking the claim is. So what we're saying is that computing an answer is as easy as verifying an answer. And this is not true for any problem, right? We all know the P not equal NP conjecture, right? But we're saying for the order K-Voronoi diagram problem, that it suffices to design an efficient non-deterministic algorithm. Okay, then you can convert that into an actual algorithm. So in non-deterministic algorithm, you have the power to guess. All you have to do is just verify. Okay, so that's a bold claim. Okay, so all right, and if you want to take another perspective, okay, so here we're basically reducing a problem to a decision problem. So verification is a decision problem. So in computational geometry, there is a well-known technique for reducing optimization problems to decision problems, okay, namely parametric search, okay? So that's a technique that's already a bit crazy if you know how it works, okay? But here it's order of magnitude crazier because in parametric search, we're searching for just one real number, and here we are searching for an entire planar subdivision, okay? And in parametric search, you lose extra log factors. Here, the claim is that runtime does not blow up, okay? At least in this case for order K-Voronoi diagrams.
So Timothy, one question.
Yes.
Yeah. So this claim is saying that if you have a non-deterministic verifier, then you have a quadratic time randomized algorithm. Does it imply anything from the deterministic algorithm?
Unfortunately, right now, the reduction is randomized. And it's because it will use Ramos's recursion. And we already have used his recursion to convert to decision trees. And his self-reduction is randomized. And that's the reason this reduction is randomized.
Okay, thanks.
Okay, so how to prove this? Okay, so the proof will be inspired by ideas from my previous paper with David on half-crash problem. which in turn was inspired by an old paper by Fredman on the decision tree complexity of sorting. In a sense, what we're doing is generalizing the framework from our previous paper, and at the same time simplify the framework. So if you have tried to read and failed to understand my previous paper on half-graph, this is a good chance to understand really what's going on, because I think the simpler presentation here might be more accessible. Okay. All right. So as I said before, it suffices to look at decision tree. So that's what we're going to do. Here is the approach. Okay. So the idea is to view our input as a point in a very high dimensional space. Okay, so remember the input to our problem is what? 2n real numbers. Okay, so it can be viewed as a point in 2n dimensional space. Okay, so to solve the order K-Voronoi diagram problem, we need to make comparisons of the following form. Is one input point inside the circle through 3 other input points. Okay, and this is essentially membership in some semi-algebraic set of constant degree. Now there are n to the 4th number of possible comparisons we could make of this form, right? And so we have n to the 4th number of such semi-algebraic sets. And what we're going to do is build the arrangement of all these sets, okay, in 2n dimensions. Okay, so as a first step. Okay, so how many cells do we have? Well, a naive upper bound will be 2 to the n to the 4th, but by the famous theorem by Milnor and Thom, you know that the number of cells is actually upper bounded by a smaller quantity, namely the number of sets raised to the power that is proportional to the dimension. So in our case, it will be n to the order n. Okay, and this fact will be extremely important for us. Okay, so remember this. Okay, so as a first step, we're going to pre-compute this high dimensional arrangement. And this is already pretty crazy. Okay, I mean, you don't usually build high dimensional arrangements like this to solve a 2-dimensional problem, right? Okay, and also if you want to build such high dimensional arrangements, the cost will be humongous, because the runtime will be super exponential. Okay, the size of the arrangement is super exponential already. But remember, we're looking at the decision tree complexity, right? So right now, the cost in the decision tree model of what we're doing so far is 0. Okay, because we're not even looking at the input. We haven't looked at the input yet. Okay, right? Okay, so then as the algorithm proceeds, we'll maintain a list of so-called active cells. So these are cells that could potentially contain our input, XP. Okay, initially, all cells are active. As the algorithm progresses, the number of active cells will get smaller and smaller. Okay, so one observation, notice if you have 2 inputs that are in the same cell, then they have the same order K-Voronoi diagram. Okay, because the order K-Voronoi diagram is determined completely by the outcomes of these comparisons. Right. So keep that in mind. All right. So now we're going to describe the actual algorithm using the verification oracle as a subroutine. Okay. And the whole thing is not long. Okay, so it will fit in this single slide. Okay. Okay, but the ideas are quite tricky, so feel free to ask me questions as we go. Okay, so the very first step is we're going to apply Ramos's recursion. Okay, again. Okay, so this time twice. Okay, and that will allow us to reduce our problem to n squared over b squared subproblems of size b, where b is log n. Okay. So then what we're going to do is solve each of the subproblems one at a time. Okay, in some arbitrary order. I don't care. Okay. So then for the ith subproblem, pi, how are we going to solve the problem? So here's what we're going to do. The first step is we're going to scan through all currently active cells. And for each active cell, we're going to generate its answer. Okay. And remember, as I said, input in the same cell have the same answer. Okay. So let's do that. And this costs us 0. So again, because this is not dependent on the actual input. Okay. So for each cell, generate its order K Voronoi diagram, the order K Voronoi diagram of PI. Okay. All right. So then we gather this list of answers, and we're going to pick the most popular answer. So the answer that occurs most frequently in this list. Okay. And we're going to run the verification oracle on this answer for PI. Okay, so now this is going to cost us something, and by our assumption, the cost, the runtime is b squared. Okay, and now if the answer is yes, then everything is good. So we have the answer. Okay, but if the verification algorithm says no, yes.
Unlikely in this when you say pick the most popular answer.
So most popular meaning the answer that occurs most frequently in the list generated in step 1.
And it's very unlikely there'll be a tie for.
There will be potentially answers that are identical because so when I say 2 answers are the same, I mean the planar subdivision is structurally the same.
Okay.
Okay.
Right.
So you will see that there are many potentially common answers. Okay, so what is an answer? So an answer can be encoded in what? So the Voronoi diagram has b squared size, so it can be encoded in b squared log b bits. So it's a string with b squared log b bits. Okay, so when b is small, you will expect actually many duplicates. Okay, so we pick one that has the largest frequency. We're going to guess that as the answer for PI. So we're going to run the verification algorithm on this guess, and the answer is yes, then we have the correct guess, we have the correct answer. But if the verification says no, then unfortunately we have to switch to a slow algorithm, okay, to compute the actual answer. And I don't care which slow algorithm you use, so as long as it runs in poly B time, then it will be fine as it turns out. And then that's the whole process. Okay, so as you go on, then you go on to the next problem. Okay, so the list of active cells will shrink as you go along. Okay, and each round you pick the most popular answer, and you run the verification on that. Okay, so that's the whole procedure. But what's not clear is that in the no case the cost is large. Okay, but the claim is that you enter the no case. You can bound the number of times you enter the no case. You cannot do the no case too often. Okay, because each time you enter the no case, I claim that you're making progress of some kind. Okay, of what kind? Well, I claim that if you are in the no case, then that you're making progress in reducing the number of active cells. Why? Because all the cells that has its answer being the most popular answer will be ruled out, so they are no longer active. We can mark them as inactive, right? Okay, because we rule out the most popular answer, then all the active cells that has that as the answer will not be consistent with our input, and they are now inactive. Okay, so how many cells have we ruled out? Well, remember there are as I said, an answer can be encoded in b squared log b bits. Okay, so there are like poly b bits needed to represent an answer. So there are at most 2 to the poly b different answers out there. Okay, 2 to the poly b answers, and the most popular answer will occur in at least a fraction of 1/2 to the poly b. Okay, and we rule that out. So the number of active cells is decreased by a factor of 1 minus 1/2 to the poly b. Okay, so it's a fraction that is only slightly less than 1, but it's still a reduction. Okay, and then the claim is that you cannot do the no case too often, because if you reduce the number of active cells too many times, then eventually it will be down to 1 and you're done. Okay, so how many times can you decrease number of active cells by this factor? Well, it's log of the number of cells with base 1 over f. So then this counts the number of iterations that we can do in the no case. Okay, so the total time is n squared for the overhead for Ramos's recursion, and then b squared times n squared over b squared for the yes cases. Right, because there are n squared over b squared subproblems where each you spend b squared time, right? And then the cost of the no cases, well, it's poly b, but it's done log base 1 over f times the size of the arrangement, number of times, right? So then that's the total cost, okay? So of course, the first two terms sums to n squared. What about the last term? Well, log base 1 over f. So you get 2 to the poly b factor here, which seems huge, but remember b is very tiny, okay? And then log of the size of the arrangement. What's the size of the arrangement? We have said by a Milnor thumb, it's n to the order n. So this is n log n. So the second term is actually small. It's less than n to the 1 plus epsilon. So it will not dominate. So the total cost is n squared. And then we're done with the first part. Okay. So any questions? Okay, so it's very slick. Okay, so what's unusual about this is that is that we are not really using any specific property about the order K Voronoi diagram. Okay, other than the existence of a self-reduction like Ramos's recursion. So it's kind of general and abstract. Okay, so if you can solve the verification problem, now we will be able to solve the original problem. So then from now on, suffices to try to design a good verification algorithm for the problem. Okay. All right. Feel free to stop me if you have questions. Again. All right. So great. Then now the second part, how to solve the verification problem. And now things will get back down to earth. So no more crazy stuff. Okay, so no more high dimensional arrangements, no more decision trees. We'll design a traditional algorithm to solve the verification problem. Okay, so problem of verifying whether a given diagram is a correct order K Voronoi diagram. Okay, so actually there were some previous papers on verification or certification algorithms in computational geometry by researchers like Kurt Melhorn and others, motivated by algorithm engineering. So the idea of coming up with efficient verification algorithm or a simple verification algorithm is important in that context. So for certain problems, there are simple verification algorithms. Okay, so like for convex hulls, for standard Voronoi diagrams, for verifying a triangulation, and so on. But verifying an order K Voronoi diagram or verifying the K level, that's a lot trickier. Because if you're talking about convex hulls or standard Voronoi diagrams, you only need to check some local conditions. Okay, but to verify an order K Voronoi diagram, local conditions will not suffice. So what you could do is maybe take an existing algorithm for constructing order K Voronoi diagram and see if you can simplify or speed it up if you just want to solve a simpler verification problem. So for example, we have tried to modify Ramos's algorithm based on cutting and see if you can turn that into an n-squared verification algorithm, but we can't do it. Okay. We could also try maybe modifying Chazelle and Adel-Spooner's algorithm, which is simpler. And in fact, we managed to, we think we can modify it to get a verification algorithm running in n-squared alpha n time. Okay, So that's alpha inverse Ackermann. So I don't know how you feel about speeding up log star to alpha, but that doesn't sound as impressive as completely getting rid of all extra factors. So we end up designing a different, totally different verification algorithm by using divide and conquer, but not in the traditional way using cuttings or random sampling, but by using planar graph separators, interestingly. So in hindsight, once you realize you should use planar separators, the approach is not that difficult to think of. Okay, so here is how it works. So remember, the input is an actual diagram, which may or may not be correct. So it may not be the actual order K-Voronoi diagram. So first thing we're going to do is we triangulate it, okay? And then the number of triangles denoted by F will be n squared. That's the size of the diagram, okay? And I guess technically you have to verify that this is a valid triangulation, but there are simple ways you can verify a triangulation. Okay, so then what we're going to do is we're going to apply the planar separator theorem, compute a cycle separator, which has size square root of F. Okay, and then you do the natural thing. You first verify all the edges in the separator, and then you just recursively verify the inside and the outside of the separator. Okay, so then that's a general approach. Okay, let me explain now more details about how you verify the edges of the separator. Okay, so and this is done by ray shooting. Okay, so you first lift the problem to 3D, so that, as we have said, it's the same as K levels for planes in 3D. One known approach is you can do ray shooting to go from one K level vertex to an adjacent K level vertex. Okay, and to be a bit more precise about what the ray shooting problem is, you can divide the input planes into two subsets: the planes that are below the current point, and the planes that are above. So for the planes that are below, you're looking at the upper envelope, and for the planes above, you're looking at the lower envelope. And you do ray shooting for the two envelopes and see which one you hit first. And then that gives us the next K-level vertex. Okay, so that's a standard approach used by Agua and Matuszek. And as you jump from one vertex to the next, actually one of the planes will move from one subset to another. So what you actually need is a dynamic data structure for ray shooting in upper or lower envelopes of planes. Okay, and in the dual, this is the same as dynamic 3D convex hull queries. And so if you use the latest results on dynamic 3D convex hulls, then you get polylog time per query and update. And since there are root-f edges you're verifying, so root-f operations, you're doing the runtimes about root-f times polylog. Okay, so verifying edges of the separator is can be done by old ideas. Okay, so then are we done? Well, not quite. So the next question is, how do you recurse? Okay, so in particular, which points should be assigned to the subproblem for the inside, and which points should go to the subproblem for the outside? Okay, and could there be points that could contribute to both the interior and the exterior of the separator? And if so, how many? Okay, and to answer these questions, I'm going to digress a little bit and talk about one simple but important observation about order K-Voronoi diagrams. Namely, if you fix one point and look at all the edges of the order K-Voronoi diagram that involves that point, that is defined by that point, like this. Okay, defined everything that's defined by the point number 4 here, then what you see is a connected polygon. Okay, in particular, it's a star-shaped polygon. So hopefully, by looking at the example, you'll be convinced. Okay, and you can do that for any point. Okay, so if you switch to say point number 6 here, then you get another star-shaped polygon. Okay, but in this case though, technically the boundary is not connected, unfortunately. And that's because the polygon is unbounded. But there are ways to fix this technicality. So you can insert some points near infinity to ensure that the polygon is bounded. Then the boundary will be connected. Okay. All right, so if you want to see why this is true intuitively, here's very, very quick, brief proof sketch. You can lift to 3D, and then what we're looking at, as I said, is k levels of planes. And then the point P is mapped to a plane. So we're basically looking at a k level within that plane. Okay, so it's a 2D k level, and in 2D, k levels are connected. End of proof. Okay. But this is not quite true in general, so you have to be careful because you're talking about k levels in 2D, but k levels of half planes in 2D, and you could have actually the k level being disconnected. Okay, but I claim that this doesn't happen to us because in our case, all the input planes are tangent to a paraboloid, so they are in convex position, and what that means is that actually within a hyperplane, all the half space within the plane, all the half spaces have a common intersection. So indeed, the k level will be star-shaped around a point in the common intersection. Anyways, okay, so assuming you have this key observation, okay, then we can answer our question. So there are basically for a point there are 3 cases. So if you look at its polygon, it could intersect the separator. Okay, because the point might define one of the separator edges. Okay, and for these points, then we have to assign them to both the inside and the outside. Okay, but how many such points? There are only root f of them, because the separator has size root f. And if you're not in this case, there are only 2 remaining cases. Either the polygon is completely inside or completely outside. And in the former case, if it's completely inside, then obviously we should assign P to the problem corresponding to the inside of the separator. And in the latter case, we put P in the outside. Right? And it's actually not too hard to distinguish between the inside case and the outside case. Okay, so then now we have all the ingredients needed to put together the recursive algorithm. So then you get this recurrence. Okay. And what's important is this inequality, that n1 plus n2 is bounded by n plus order root f. And that's because of exactly what I said. The only points that can participate in both subproblems are those root f points. Okay, and so all we have to do now is solve the recurrence. Now you might wonder about the polylog n factor, but the thing is that this is in front of a root f term here, and n goes down as we recurs. So if you solve the recurrence appropriately, then the polylog n factor will eventually disappear. And if you want an intuitive explanation, maybe you could maybe look at the ideal case where everything is perfectly balanced. Okay, so then at height I of the recursion tree, you have f over 2 to the I nodes with number of triangles being 2 to the I. And then the n plus root f term sums to the global n plus the global f over 2 to the I times square root of 2 to the I. And the polylog n term will become polylog of this divided by the number of nodes, f over 2 to the I. So that's the average n for the nodes at that height. Okay. And the important thing to note is that we're taking polylog of something that is exponential in I. So the polylog actually becomes polynomial in I. Okay, so that when you sum over all I, you indeed get a geometric series. So only constant factor blow up. in the second term. And since f is n squared, total time n squared, and we're done. Okay, so basically a simple recursive procedure using separators. And as we recursively eliminate input points so that the polylog n factor goes down, forming a geometric series. Now, and gloss over various minor technicalities. So for example, as recurse, actually you get regions with holes. And it's important to ensure boundaries are connected so that you can do ray shooting. And also, do you want square root of f for the boundary complexity of every region? Actually, you don't. It suffices to have good average bound on the boundary complexity. Also, we have overlooked the cost of computing the separator. And computing one separator might take linear time, but you're computing a whole hierarchy. And if you're not careful, then you get f log f, which we don't want. But all these issues can be fixed if you just apply or invoke the right known results on planar graph separators in the literature. Okay. All right, so then we are basically done. So last slide. So some final remarks. So we have come up with the first optimal algorithm for order K-Voronoi diagram, but it's pretty complicated. Are there simpler algorithms? Do we really need all that crazy stuff? Okay. So for example, if you read the Agua-de-Burg Matrushik-Schwarzkopf paper, they actually conjectured that their simple randomized incremental algorithm runs in optimal time. Okay. But for over 20 years, no one has improved their analysis. And I personally don't see how you can get rid of the extra log in their method. Okay. What about deterministic algorithms? So as I said, actually the only part that uses randomization is Ramos's recursion. So everything else is already deterministic. And also the idea of verification algorithm or non-deterministic algorithm is quite interesting in its own right. Can you study verification algorithms for other problems in computational geometry? And in the crazy part, we have a pretty general way to reduce a problem to of the verification problem. So are there other applications of this idea of using non-determinism? Unfortunately, the crazy part is quite general, but it requires a self-reduction similar to Ramos's recursion. And if you have that kind of recursion, you already have something that is close to optimal, being within 2 to the log star from optimal. So you're looking at for problems that have pretty small gap, okay, of log star factors that you're shaving. And there are not that many problems in the literature, unfortunately. But still, there might be potential also for applying the idea to problems where we want not to improve log star factors, but actually go below n squared. So there's a well-known major open problem of trying to determine whether there exist collinear triples. Okay, affine degeneracy testing in 2D, whether that problem can be solved in n squared, less than n squared time or less than n squared decision tree complexity. Okay, so what our technique shows is that if you want to solve this problem, so first of all, this problem does have a self-reduction like Ramos's recursion. So what our technique shows is that it suffices to consider non-deterministic algorithms to solve this problem. Non-deterministic algorithms that can verify both yes and, more difficultly, no answers in subquadratic time. But unfortunately, I don't know how to get subquadratic even if you have the power of non-determinism. So for this particular problem. Okay. So I think I'm done now. Okay, so thanks for your attention.